So we'll proceed. What we did in the last segment was look at the behavior of higher order modes and also introduce this notion of consistency of the finite difference approach to time discretization. I ought to mention that the proof of those results for consistency and order of accuracy are obtained by essentially looking at the time exact solution, carrying out Taylor series expansions and finite Taylor series expansions, and then manipulating them. It's a fairly straightforward exercise, but somewhat tedious. Okay, so in this segment we are going to essentially move to the end game for this particular topic. We are going to look at convergence. Okay, so we're going to look at convergence of the time discrete solution. All right. In order to talk of convergence, as you may recall from our early treatment of error analysis for this finite element method itself, we need first to identify what our error is. Okay, so we define the error, and as we've done before in the context of the finite element solution itself, we will define the error as the discrete solution, right? But in this case, we look at the discrete solution at n plus 1 minus the time exact solution at n plus 1. Okay? All right. Now, this is what we define as E at n plus 1. Okay? Now, En plus 1, of course, is just another vector in the same space, right? Right? Just as D and T are, Dn plus 1 and D at Tn plus 1 are vectors in this RNDF space. But what that means is that because we have a basis, our orthonormal basis, we can expand E as well in that basis. Right? So we can essentially carry out a modal decomposition of E at n plus 1. Right? And that modal decomposition essentially is that E at n plus 1 equals sum over m, E m for the mode at n plus 1, right? Those are our scalar modal coefficients times psi m, all right? Just as for any other vector. Okay, now how do we pose the question of convergence, right? We say that something has converged, right? Or we say our solution has converged, convergence right, is the requirement that as the limit of n plus 1 tending to infinity, right, as we take more and more steps, right, what we expect to see is that E n plus 1 dotted with m E n plus 1 equals 0, right? That limit is 0. Okay? Can you tell me why it is okay to, or can you think why it is okay to put m inside there? Normally one would say that, well, the error has to vanish, right? But why is it okay to put m in there? It's because m is positive definite, right? Right, so let me just state this here. Since m is positive definite, right, what we see is that E n plus 1 dotted with m E n plus 1, right, equals 0 if and only if E n plus 1 itself equals 0. Okay, only if it's only when that vector itself is equal to 0 that that quadratic product is equal to 0, since m is positive definite. And so, and this is why it means that, well, yes, if this particular limit is tending to 0, it has to be that E itself, E n plus 1 itself is tending to 0. Okay, so this is why it's okay to consider this as our convergence criterion, right? But more importantly, we are not going to work in this form, right? We're not going to work with E dotted with ME. We're going to work in terms of modal coefficients because our entire analysis has been in terms of modal coefficients, right? But it's okay because I'm going to show that for this quantity tending to 0, right, this quantity that I put a brace on, okay, that quantity tends to 0 only if the modal coefficients themselves go to 0. Okay, so let me, I've told you what I'm going to show you, but in order to write it out, let me say the following, but note the following. Okay, E n plus 1 dotted with m E n plus 1 equals sum over m E m n plus 1 psi m dotted with m sum over L E L n plus 1 psi L, right? And I'm going to put parentheses here. Okay, each of those sums is for one of those E's, right, in the quadratic product. All right. Okay. Well, we know how this works now. This is equal to, let me see how I want to write it. Right. It is the sum over m and L, right, of em n plus 1 psi m dot m psi L, right, and for no particular reason I'm going to put parentheses around that, and here I have E L n plus 1. All right. However, we know that this is delta ml because of the orthonormality of the size with respect to m. Right? Well, if that is the case, we know that this product that we started out with, E n plus 1 dotted with m E n plus 1 equals sum over m E m n plus 1 E m n plus 1. right? Essentially what has happened there is that the Kronecker delta has been used to turn that L index into an M index, right? So this is basically just the Euclidean norm with respect to the psi basis, right? So this is sum over M, Em n plus 1, the whole square. Okay, so now it's clear that if this quantity is tending to 0, it means that the modal coefficients, that sum itself has to tend to 0, right? Which means the modal coefficients themselves have to go to 0. Okay, so what this implies finally is that limit n plus 1 tends to infinity n plus 1 dotted with m e n plus 1 equals essentially limit as n plus 1 tends to 0, tends to infinity of this sum. Okay, all right, so clearly if this has to be equal to 0, if this limit is equal to 0, it just means that every single modal coefficient tends to 0. Okay, all right, so limit n plus 1 tends to infinity n plus 1 dotted with m n plus 1 equals 0 if and only if each n plus 1 equals 0 in the limit. Right? So it means that it's okay to just look at what happens with the modal coefficients. Okay? Right? So study convergence of modal coefficients right, E n plus 1. Right, I'm now dropping the explicit mention of the modal index. Right, I've just dropped m. Okay. All right, well, that's what we're going to do. Okay, so how do we set it up? We set it up by going back and writing out our time discrete equation, our modal time discrete equation in the form that we set up in order to pose the question of consistency. Right? So here's what I say. Consider the time discrete equation in the following form. D n plus 1 minus a dn minus ln equals 0. Okay, and consider the exact equation also forced into this form. We know, however, that the exact equation does not cooperate and give us a 0 right-hand side. Instead, we get delta t tau at Tn. Okay? Right? What I'm going to do now is subtract the second equation from the first. Okay, so I'm going to change signs. Okay? And now when I add those two together, I get on the left-hand side, right, dn plus 1 minus d Tn plus 1 is essentially our E at n plus 1, right? Okay, right? It is the error in the corresponding modal coefficient, right? And here I get minus A E at n, right? The ln's cancel out and I'm left with minus delta t tau at Tn. I'm going to rewrite this as an expression that will allow me to write out a recursive formula for the error. Error at n plus 1 equals A times error at E minus delta t tau at Tn. Okay, I'm going to use recursion now and write from here E at n equals A E at n minus 1 minus delta t tau t n minus 1. Okay? But what that implies is that on substituting E as written here in that expression, right, I get E at n plus 1 equals A square E at n minus 1 minus A to the power 0 delta t tau at Tn minus 1. Okay. Right, minus A to the power 1 delta t tau Tn minus 1, and I just realized that here it is just Tn. All right. Now I can take yet another step. Okay. What if I were to now rewrite an equation for En minus 1? Right, I would get A E n minus 2 minus delta t tau at T n minus 2. Okay, and making the substitution, right? You see how this is going, right? What I would get is that E at n plus 1 equals A cube E n minus 2 minus A to the 0 delta t tau Tn minus A to the 1 delta t tau Tn minus 1 minus A square right, minus A square delta t tau at Tn minus 2. Okay, now one can go on with this, and I'm sure you've all done it at one stage or the other with similar expressions. When you go all the way back to the 0th step, right, or the initial time, we get E at n plus 1 equals A to the power n plus 1, okay, right, A to the power n plus 1 E at 0, okay, minus sum I going from 0 2n e to the power I delta t tau at t n minus I. Right? You can check that this is what the recursive formula reduces to. Okay? All right, let's stare at this. What is E at 0? What is the error at time t equals to 0? It's equal to 0, right? Because we've made sure that our initial condition is actually obtained from the time exact solution, right? I mean, at the initial time, there is no error, right? Because we fixed the initial condition.